In this video, we're going to talk about spanning sets and a span. First, we're going to define what a span of a set of column vectors is. So there's a couple of things that we need to note, is that S is a finite set of vectors. It is the spanning set. They, with their linear combinations, produce the span. So this with these brackets here means that it is all the linear combinations of this finite set. The span is infinite because to get to the span, you take these finite vectors, you do linear combination, so your scalars multiplied by each one of the vectors. And when you do the scalars times each of the vectors, you're going to get a new vector, but that new vector is in the span. The spanning set is the finite. The span is all of the vectors, and it's infinite. So let's take a look at an example. What the heck does this mean? So we're going to consider these three vectors, u sub 1, u sub 2, and u sub 3. Those are the spanning set. I'm asked to determine if this is in the span of S. So they're asking me, is W an element of the span? The way in which I do that is I look to see if alpha sub 1 multiplied by my first vector, which is 2, 0, 0, plus alpha sub 2 multiplied by my second vector, 4, 1, and 6, plus alpha sub 3, now these are my scalars, multiplied by negative 4, 0, 7. When I do this linear combination, does it equal to negative 1 and 1? So even though these are just vectors and they're not a linear system, I'm going to use a linear system to solve this. So what I'm going to do is I'm going to put my first row, as I know from my previous theorems, I can use my first column, excuse me, not row, but my first column can be replaced with my first vector. My second column can be replaced with my second vector, my third column with my third vector, and I can augment on what I hope to find here, and that should be a positive 2, what I hope to find to be the answer. I'm asking myself, if I take alpha sub 1 times the first vector, alpha sub 2 times the second vector, and alpha sub 3 times the third vector, do I get my W? That's the question. That is the question of the day. So I go ahead and I reduce row echelon form this this matrice. And when I put this in reduced row echelon form, I'm going to get this matrix, which is 1, 0, 0, and 5. I get 0, 1, 0, and negative 1, 0, 0, 1, and 1. So this tells me, because my number of pivots, R, is equal to 3, my number of columns is equal to 3. That means that there is one solution for alpha 1, alpha 2, and alpha 3. That solution comes from each one of these rows. So this first row tells me that alpha sub 3 would have to be 1. This would tell me that alpha sub 2 would have to be negative 1. And this tells me that alpha sub 1 is equal to 5. That tells me that if I go back up here and I replace this with 5, I replace this with negative 1, and I replace this with 1, that I could do the linear combination of 5 times 2 minus 4 more gives me 2. 5 times 0 is 0, minus 1 plus 0 is negative 1. 5 times 0 is 0, negative 1 plus negative 1 times 6 plus 7 gives me 1. So I found that there is only one way, one linear combination of my three vectors to get this particular vector. So the answer is yes, this is an element. That is true. It is an element. W is an element of the span. Now remember, the span is infinite. I could have had any alphas to get a different vector, but they wanted in particular this vector. Now let's take a look at this example here. They're asking me again whether or not this vector is in the span, and the span is built from this spanning set. The first vector A1 and the second vector A2. So A1 and A2. So what they're asking me to do is alpha sub 1 times my first vector, which is -4, 4, and 3, plus alpha sub 2 times my second vector, which is 2, 8, and -7. And I'm asking whether or not, if I can do a linear combination, I can get -10, -8, and 7. Because the question they're asking me is W in the span, or in other words, the set of vectors that are spanned by these two vectors? So once again, I'm going to go ahead and put this into a matrix, an augmented matrix. So my augmented matrix will be -1, 4, 3, 2, 8, -7, augment on the -10, -8, and 7. I'm going to reduced row echelon form this matrix. And when I do that, I get this matrix, which is 1, 0, 0, 0, 1, 0, and 0, 0, 1. Now, the number of pivots I have is 3. 1, 2, 3 pivots. The number of columns, or the number of vectors I have, is 2. Because R is greater than N, the answer is no. W is not in the span generated by this spanning set. So let's go on to some definitions. Let's take a look at this first definition. The theorem of a spanning set for null spaces. So you read through it and it's pretty cool, and you're thinking, but we kind of do that? Yes, we did it, but before, what we did is that we were using the spanning set, or we weren't doing the spanning set, we were talking about the null space, and we were talking about homogeneous systems. In this theorem, it is for any matrix that is a row M and N columns. It's any one. And when I reduce row it into reduced row echelon form is my equivalent B matrix. And this is going to tell me about my null space. So this is generic, whereas our previous one was in reference to homogeneous systems. Now it's saying it doesn't have to be a homogeneous system. It's just a matrix. So if I take this matrix and I reduce to row echelon form, what I end up with for this particular matrix is the matrix here is going to be 1, 0, 4, -5, 0, 1, 2, -3, 0, 0, 0, 0. The number of pivots is 2. The number of columns, or vectors, happens to be 4. So what we know is my D is going to be in the first column and the second column, and my F is going to be in columns 3 and 4. That tells me my null space is going to have 2 vectors besides the 0 vector, and nobody cares about the 0 vector. So how do we find the null space using the stuff that we've learned in the past? We know from this row right here that alpha sub 1 plus 2 alpha sub 2, let me have my subscripts here correct. Let me erase that. It is alpha sub 2, 2 alpha sub 3 minus 3 alpha sub 4 is equal to 0. Alpha sub 2 is equal to -2 alpha sub 3 plus 3 alpha sub 4. So when I start thinking about my null space, let's go ahead and build that, is I'm going to have my x sub 3 and then I'm going to put in the entries as the coefficient of the null space. My first row here gives me alpha sub 1 plus 4 alpha sub 3 minus 5 alpha sub 4 is equal to 0. Alpha sub 1 is equal to negative 4 alpha sub 3 plus 5 alpha sub 4. So then I have the plus, this is x sub 4, actually I should probably do alpha, this is alpha sub 3, and this is alpha sub 4. Okay. My entry on my first column on both vectors are going to be the coefficients on the alpha 3 and the alpha 4. So I have negative 4 and 5. The second position in both of my vectors are going to be the coefficients on alpha 3 and alpha 4. So that is negative 2 and 3. My third position, I would expect to have a 1 in the alpha 3, but alpha 3 is not defined by alpha 4, so that will be a 0. So 1 and 0. In my alpha 4 position, or excuse me, in my fourth position, I would expect that my fourth position would be 0 for my x sub, or alpha 3, and 1 for my alpha 4. Now that I've done that, then I have the null space of A, which is equal to, this is my z1 vector, this is my z2 vector. So this is equal to z1, z2, or in other words, it is my first vector of negative 4, negative 2, 1, 0, and my second vector of 5, 3, 0, 1. All right. So let's take a look at our next example here. Suppose we have these 4 vectors. And with these 4 vectors, what I'm asked to do is to determine whether or not y is in the span. Now here's some notation, so pay attention to this notation. They're telling me W is the span. So W is all of the linear combinations of these 4 vectors. So let's go ahead and do row 1, or column 1, column 2, column 3, column 4, my what I'm checking to see if I can get a linear combination of. Okay, and I can tell right out of the way, I've got some, without doing any work, I have 3 equations, and I don't have 3, I have 3 equations, but I have 4 columns. I have 4 possible vectors. So let's go ahead and RREF this, reduced row echelon form, and we end up with, my first column is 1, 0, 0. My second column is 0, 1, 0. My third column is 2, 1, 0, 3, negative 1, 0. And my third column, or final column, excuse me, is 2, negative 1, and 0. So what does this tell me? Well, the first thing it tells me is that I have, my number of pivots is 2. My number of alphas, or the ones I'm trying to find, is going to be 4. So I have my pivots here and here. So my D is in columns 1 and 2. And my F is in columns 3 and 4. So let's start building the system then, or the null space. So what I end up with in this first row is alpha sub 2 plus alpha sub 3 minus alpha sub 4 is equal to negative 1. This one gives me alpha sub 1 plus alpha sub 3 plus 3 alpha sub 4 is equal to 2. From this, I'm going to build first my constants, and then plus my alpha sub 3, because that is my free variable, and then alpha sub 4, because that's also my free variable. Okay, I need to take this, and I need to solve for alpha 1. Alpha 1 is equal to 2, that's my constant, so that's 2 is going to go there, minus alpha sub 3, so that's going to be a negative 1 there, and then minus 3 alpha sub 4, so negative 4 goes there. I'm going to go ahead and solve for alpha 2. Alpha sub 2 is equal to negative 1, so that goes in the constants. And then minus alpha sub 3, so a negative 1 goes there. And then plus an alpha sub 4, so that's going to go there. My free variable, which is alpha sub 3, is going to be 0. It's going to be 1 in terms of itself and 0 in terms of 4. My alpha sub 4 has no constant. It has no alpha sub 3 because it's a free variable, so it won't be in terms of the other one. And it has 1 in alpha sub 4. So my null space of A is going to be equal to, in this case, Z1, Z2, and Z3, which is going to be equal to 2, negative 1, 0, 0, negative 1, negative 1, 1, 0, and my last vector, which is negative 4, 1, 0, 1. So what this tells me is that I can get to my vector W, and it is, by the way, yes, the answer is yes, W, that Y, my vector Y is in the span. And the way I can get there is either taking this one, which is 2 times my first vector. I'm going to call each one of these vectors U1, U2, U3, U3, and U4. So I can do 2 times vector U1 minus U2, and then plus 0 U3 plus 0 U4, and this is going to give me one of the ways in which I can find my y vector. Another way in which I can find my y vector is this one, which is negative U1 minus U2 plus U3 plus 0 U4, and this is going to also give me a combination to get me to y. Lastly, looking at this, I have negative 4 U1 plus U2 plus 0 U3 plus 1 U4 is going to give me my y vector. So there are 3 different ways, 3 different linear combinations that I can get by using my vectors U1, U2, U3, U4 to get to y. So to answer the question, is this in there? And the answer is yes, and there are 3 ways to get there. Now, let's take a look at the fact that I have these vectors, and I'm just going to rewrite these vectors over here, and let's talk about, can I make my spanning set to be less vectors? So I have negative 1, 2, 1. I have 3, 1, 2. I have 1, 5, 4. I have negative 6, 5, 1. Now I'm going to put this into a matrix, and I'm going to row reduce this matrix to determine whether or not I can write my spanning set with less vectors. So as before, I am going to reduce row echelon form this matrix. And I'm going to get, in the first column, I'm going to get 1, 0, 0. I'm going to get 0, 1, 0. 2, 1, 0. 3, negative 1, 0. Now, as before, My pivots are 2, my columns are 4. So again, what I know is that my D is going to be column 1 and column 2. My F is going to be column 3, column 4. So if I look at just this vector, then I'm going to get my null space, or excuse me, just this matrix. If I call this matrix A, then my null space of A is going to be defined as, I don't have any constants, so I don't have to worry about that. But my first vector is going to be -2, -3, -2, -1, 1 and 0. And then my other one is going to be -3, +1, 0, 1. Okay. Now what does this tell me? Well, this tells me that if I do -2 times my first vector, -1 times my second vector, so u1, u2, plus u3 plus 0, u4 is going to give me 0. So in other words, I have u3 can be wrote as a linear combination of 2 u1 plus u2. So I can take u3, which is my third vector, and I can write it in a linear combination of vectors 1 and 2. So that tells me that I can take my span and I can eliminate my third vector. So my span right now is what I thought my span to be, my spanning set, My spanning set I thought to be was u1, u2, u3, and u4. So the fact that I can write u3 as a linear combination of u1 and u2 means that I don't need to have u3 as part in my spanning set. And that comes from this. Now let's do the second one here. Now what I have is -3 u1 plus u2 plus 0 u3 plus u4 is equal to 0. u4 can be wrote as a linear combination of u1 and u2. Because it can be wrote as a linear combination, I don't need that in terms of my spanning set. So my spanning set that started out with 4 vectors really can be reduced down to just 2 vectors, which is u1 and u2. That means, since I've gotten from 4 vectors to 2 vectors using homogeneous systems, and what we learned from homogeneous systems, that if I were to check whether or not a vector is in the span, I can just look at just these 2 vectors, which are truly my spanning set. And I can look to see if I can get from my spanning set to my span and get that vector to see if that vector is in the span. So that's it.